about, well, strain control of quantum materials.
Well, thank you very much. Good morning. Thank you to our hosts for such a wonderful place to come. So, all right, good. So strain control of quantum materials, fine. I was going to talk about the case of multipolar order. And given the talks that we've had already, I want to, right from the start, be clear, this is talking about local atomic multipoles, not constructed by some larger object inside the unit cell. And this is talking about spontaneous order associated with those multipoles, not developing, for example, a dipole on top of a quadrupole or something like this. Okay, so the two specific materials that I'm going to talk about are thulium vanadate and praseodymium vanadium aluminum. And although I've chosen these two, the principles I'll talk about are much more broadly applicable. So, all right, so thulium vanadate, this is the crystal structure here. These sort of coordination polyhedra things, that's the VO4 clusters. The thulium ions is where all the excitement comes. These are the purple ions. And below 2 Kelvin, each one of these thulium ions develops a spontaneous quadrupole, electric quadrupole moment, which I've projected down into the basal plane here. And so that's a ferroquadrupole order. Right. In the case of praseodymium vanadium aluminum, right, this is a more complex structure. It's a cubic structure. There's no point in me drawing it. It's just a complicated structure. But the praseodymium ion, the multipole that we're talking about here, is a magnetic octupole. And good, there's a magnetic octupole. All right, so what I'm going to do is motivate why you might care about these things, talk about effective fields for multipoles. We've heard parts of this in Elena's talk, and see the special role for strain in that context. And then I want to specialize to look at first some longitudinal field effects. And here, longitudinal fields, all right, so that's going to let me define a susceptibility. So the susceptibilities of these multipoles. And then talk about some transverse field effects, and indeed how, particularly for the case of the thulium vanadate, this can map onto the transverse field Ising model, but where coupling to the nucleus becomes incredibly important in terms of the quantum phase transition, and there's an electronuclear quantum phase transition. So that's where I want to go with this. Okay, a number of people from my group have contributed to this, but I do want to point out particularly Mark Zeek and Linda Ye for the majority of the work that I'll show you today. We've also done experiments. I'm not sure if many of you have been to the Mag Lab in America, but the High B over T facility has a very low temperature refrigerator you can use, and so we've been there to do some experiments too. I'll show you some ultrasound measurements from Brad Ramshaw's group, and then theory. All right, well, maybe I'm standing here because I know Raphael, but we've also worked with Steve and other theorists on these things. All right, so let me give you first just an initial comment about using strain in general. So already, great, you can do strain engineering of band structures, these kind of things. My own interest is just in coupling to order parameters, so coupling to different physical ordered states that a system might have. And if you want to think along those lines, there's always going to be a trivial coupling, where strain, which doesn't break a symmetry of the Hamiltonian, and I tend to live in tetragonal materials a lot, so it'll be an A1G representation, that will always couple to the square of the order parameter, which belongs to some irreducible representation of the point group, call it gamma. Right, so there'll always be a trivial coupling like this, or of course biquadratic couplings between strains of any symmetry and the order parameter. But all this is going to do is renormalize or change the critical temperature. And so here, for example, here's a material we've studied, charge density waves in erbium tritelluride. As a function of strain, this is one component of the strain tensor. You can tune critical temperatures, look at behavior near a bicritical point, all sorts of interesting things. Right? So you can do that. But what I want to talk about today are perhaps what you might call more non-trivial couplings, where strain either belongs to the same irreducible representation as the order parameter, or where combined with either a magnetic field or possibly a strain of another symmetry, the combination of these forms an effective composite field, which can now couple to the order parameter. So in group theory language, gamma 1 prime direct product with gamma 2 primed is gamma. All right. So in this case, strain is either a effective field or it's part of a composite effective field. And that's why I get sort of excited about these multipoles, that we can hold on to them using something at some level as simple as changing symmetries of crystal lattices. Right. If you want to go a little bit further, it also means, good, you can probe a susceptibility, you can detwin these systems if you have the effective field. And if you want to think a little ahead, all right, good, so you could also think about transverse fields which induce orthogonal states, leading to order parameter fluctuations, something that looks like the transverse field Ising model. And here, right, good. So I want to explore all that in the context of multipole order. Okay, all right, good. So multipoles, good. Local atomic charge, magnetization densities described by a multipole expansion provides a complete basis for these. And of course, we're familiar with the cases of dipole order, but spontaneous order of higher rank multipoles is perfectly allowed. It's just that, in many cases, the dipole order wins, right? So we want to find cases maybe where the dipole order isn't the dominant symmetry. But you're certainly allowed these states. It's just less common. All right. So why might you want to do this? Why might you want to study these higher rank multipole ordered states? So first of all, these are local moment realizations of more complex, sometimes itinerant states. You break all the same symmetries. For example, quadrupole order, ferroquadrupole order breaks all the same symmetries as nematic order. Or octupole order breaks all the same symmetries of some types of ultramagnetic order. We heard this in Elena's lovely talk. So, and you know, you can go up here as well. So hexadecapole order is ferroaxial order, and so on. But you can study this in a case where you know the effective Hamiltonian, because what I'm about to tell you, we're going to do this with rare earths. We know the effective Hamiltonian that describes the local atomic states on a rare earth ion. Good, all right. We also heard in Joe's lovely talk that coupling to the lattice is different in interesting ways to the case of a magnetic dipole. That leads to some very rich physics, which we heard about. Something else is that in metals, there's also some very rich physics associated with multipole fluctuations and how those couple to the conduction electrons. It takes you to interesting fixed points. Some of the work of Young-Baek Kim would be what you want to think about for that. And lastly, all right, these are actually largely underexplored ordered states and particularly underexplored quantum phase transitions. Okay. Right, so where are you going to find these states? Remember, we're talking about a local atomic state. So first of all, if I want a higher rank multipole, I've got to look at an atom which has a higher angular momentum. And then for cases that don't break time reversal symmetry, I'm also going to require non-Kramers degeneracy or pseudo-degeneracy. Right? So this is why the rare earths are the place to look. So you've got local orbitals with large total angular momenta. They alternate Kramers, non-Kramers, Kramers, non-Kramers. The ends of the series, courtesy of Hund's rules, actually have sort of minimize the pairwise spin interactions just because the S part of J is much smaller. So you're much more likely to get a higher rank multipole order with cerium, praseodymium, thulium, or ytterbium. And then lastly, a point which is can be easiest to see through example is that specific crystal field eigenstates restrict the allowed multipoles in useful ways. Okay. And then just to compare this with 3Ds, all right, good. So the rare earths have a much larger magnetoelastic coupling. So what this means is this is going to be in the opposite limit to the ultramagnetic case that we heard about with Elena. And also, all right, good, so J is greater than 2, so you can have this multipole, but living on one atomic side. All right, good. Right, so having said that, let's just look at the effective fields for these multipoles, and then I'll dive in and look at longitudinal and transverse field effects. And here I'm going to specialize to cases that preserve inversion symmetry, but I'm not losing any generality in doing that. All right, so I've got a little table. It goes dipole, quadrupole, octupole. And because we're preserving inversion symmetry, is magnetic dipole, electric quadrupole, magnetic octupole. And I'm just going to write down the multipole operators and the effective fields. All right, so for a dipole, obviously this is the angular momentum, and a magnetic field has the right symmetry to couple to this. If I go to an electric quadrupole, all right, so this is showing one of the 5 possible quadrupoles. This is the XY symmetry quadrupole. And courtesy of the Wigner-Eckart theorem, there's a, you can write down a multiple operator in terms of total angular momentum. It's always going to be bilinear combinations, right? So preserves time reversal symmetry. And so, for example, this is the operator that tells you about the XY symmetry quadrupole. Right, you see this is a headless vector or a rank 2 tensor. So strain has the right symmetry to couple to this. And so for each one of the quadrupoles, there's a strain with the right symmetry to couple to that. And so the right symmetry to couple to an XY symmetry quadrupole is an XY symmetry strain. Or, good, you could make a sort of a composite field from HX, HY. That's got the right symmetry, but it's now not linear in the physical object that I'm applying. So I will prefer to use strain here. And if I go on to the octopole, all right, so this is one of the 7 possible octopoles. I'm showing it because it's the one that's relevant for the case that I'm going to look at. It's described, so these are described by trilinear couplings of the J's, so breaks time reversal symmetry. And now nature doesn't give us a smooth, uniform object that transforms as an octopole, so I'm going to have to create this as a composite effective field. And this combination of fields and strains does the right job here for a cubic point symmetry. All right, so how do you know this? So the primary way you know this is from group theory, which is always right, and doesn't tell you about magnitudes, but just tells you what you've got to do. So you know which irreducible representation of the point group the field belongs to, the strain belongs to. You know that the direct product of this belongs to the same irreducible representation as this multipole. All right. So that's a true statement, always correct, but doesn't give me any physical intuition. So you can develop some physical intuition just by sort of looking at the symmetries of these objects. So if I draw here, imagine a doublet state corresponding to octopole up and octopole down. So these are north and south poles, if you like. This is showing magnetization density. And I want to split that linearly. So if I were to apply a magnetic field and induce a dipole, I will strengthen the north poles in this direction or strengthen the north poles in this direction, but the magnetic field doesn't differentiate these states. Nevertheless, I've got charge density, which is sort of skewed around. And so now if I were to shear this, I will differentiate between these 2 states, right? That's what this combination is doing. Or I could imagine shearing this, and that's what I'm going to show over here. So if I could pull this in this direction, I'm going to either induce a dipole up or pull here a dipole down. And again, this is not differentiated in the presence of the shear strain, but when I apply a magnetic field, it will be. Again, that's what that's doing. Right? So this is sort of the intuition behind what group theory is telling you to do. And the point that Elena made very beautifully, you don't know the strength of the coupling parameter in front of that. Group theory isn't going to tell you that. But you've got a pretty good feeling about this using rare earths because of the strong magnetoelastic coupling. Okay, you can go further along this series. So you could look at the octopole, what's the next one? Sorry? Hexadecable, thank you. So this is the m equals 4 of the l equals 4 state for a tetragonal system in this case as I was drawing it. And all right, good. So in that particular point group, this would be the operator. And all right, well, this is now a nonlinear combination of strains, but this works. And there are materials where you have ferroaxial fluctuations, which you can couple to in this way. All right. So at this point, my point is, if an order parameter corresponds to a specific multipole, then we can readily identify an appropriate effective longitudinal field. And you can also identify an effective transverse field, or fields, which would be fields that induce multipole moments, which are by definition orthogonal to the order parameter. And then because the multiple operators within any given degenerate Hilbert space do not commute with each other, that means they can induce quantum fluctuations. Right, so what we're going to have is a generalization of the transverse field Ising model, but that generalization is going to do some interesting things because of the ways these different fields couple to other internal degrees of freedom in the system. Okay. All right. So now let's meet the materials just in a little more depth of what we'll talk about. So thulium vanadate, I showed you the crystal structure. All the action happens on the purple blobs. I should have told you it's an insulator, it's tetragonal, and the thulium ion has a total angular momentum of 6. The crystal field splits that. The ground state is about 70 or 80 Kelvin away from the first excited state. All the exciting physics happens below 2 Kelvin, so the material's living in the restricted Hilbert space of just this doublet. All right. That's a non-Kramers, thulium ion. It's a non-Kramers doublet. The little e here tells you that this transforms like xz and yz. And so although this is a complicated 4f orbital, if you picture dxz, dyz orbitals, it's going to be transforming in the same way under the symmetry operations of the point group. It's a doublet, so there's a very convenient pseudo-spin representation, which I'll mention as we go on. And we know that that doublet can host one of 2 quadrupoles, either an x squared minus y squared or an xy symmetry electric quadrupole, or a z-axis magnetic dipole. And because we know what multiples it can host, we know the appropriate fields. It strains with the right symmetry for these quadrupoles, or a magnetic field for that magnetic dipole. All right. So I said very confidently this. How do we know this? This is another group theory statement. So you can get to that by a number of means. The first way is what I call brute force. This is how I first came to understand these things, is you just look at all of the multipole operators, and then you realize in that restricted Hilbert space, which one of them have matrix elements, right? That's the brute force way, but it teaches you a lot to go through this. The elegant way is group theory. This just tells you what the different irreducible representations are that are allowed to inside this, if you like, and you just look and ask which are the lowest ranked multipoles for each of these. But you can also get there if you want to be a little elegant from a quantum mechanics perspective of just looking at the Pauli spin matrices because it's a pseudo-spin. They're all the same. These are all the same thing, but it's just different ways you might get there doing the same thing by different methods. So that's how we know that. All right, so in this material, it turns out that the quadrupole interactions are stronger than the interactions between the spins. And so this orders with a quadrupole order, and it's a ferro-quadrupole order. That happens at about 2 Kelvin, and that's been known since the 1970s. All right, so if I want to look at this sort of graphically, looking down the c-axis, I have the unsplit doublet at a high temperature, and I've drawn it in the xy basis. That splits spontaneously. So now I have more population of one state than the other. So that's the XY quadrupole, drawn here in terms of the occupancy of the actual orbitals, but just showing these as XY, as sort of d orbital things. And this clearly, because of that bilinear coupling to the strain, you have a concomitant strain that develops spontaneously there. And right, great, you can measure that strain. This was also done in the 1970s. There's the development of the spontaneous strain at this continuous phase transition. Okay. You could ask, what do the fluctuations do? So up above the phase transition, fluctuations of this quadrupole are going to soften the shear mode, which develops that spontaneous strain. That shear mode is C66. And so these are measurements from Brad Ramshaw, just ultrasound attenuation measurements, showing the softening of the C66. And the only reason that in these measurements that doesn't actually go to 0 is just the ultrasound attenuation becomes so large as this lattice becomes infinitely soft to this mode. All right. So that's the first of these materials, right? The second material is praseodymium, vanadium, aluminum. All right, this is clearly a metal that's shiny. You can grow these beautiful crystals of this. This is cubic, not tetragonal. And the active ion here, obviously, is the praseodymium ion. That has J equals 4. Similarly to the thulium vanadate, this has a doublet ground state, very well split from excited states. So 70 Kelvin away, and all the action is happening at a Kelvin or so. So you're again living in a restricted Hilbert space of this doublet. But now if you ask what multipoles are allowed for this doublet in this point symmetry, you'll find it's one of 2 electric quadrupoles. So I should say again, this is a non-Kramers doublet. Or, right, the state which breaks time reversal in this case is a magnetic octopole, not a magnetic dipole. And you can see by looking at the crystal field eigenstates that you're not going to get matrix elements for Jz, Jx, or Jy in that. All right. So in this case, there's a sequence of 2 phase transitions driven by the 4F order, and the name you should associate with this is Satoru Nakasuji. And so this is work he's done in the 2000s, so a little bit more recent than the 1970s. And we know that at 0.7 Kelvin, there's an anti-ferroquadrupole transition. And there's a second phase transition at 0.6 Kelvin. The symmetry associated with that is currently unknown. But we do know, courtesy of Satoru's measurements, that there's a strong magnetostriction. And there are reasons which will become apparent that this is going to involve the octopolar degrees of freedom. So if you want to look for octopolar fluctuations, at least, this is a really good place to start. All right, so how do I think about these 2 materials? These are model material systems. Hopefully that point's sort of coming across. In this case, to study multipolar order, I would say there's sufficient complexity to be interesting, but sufficient simplicity to be tractable. And that's what, in my mind, makes a model system. And in this case, the model part, this is all coming in a way because of that doublet ground state, which restricts the possible multipoles, that point I was making, and then permits, all right, good, this very elegant and simple pseudospin representation. All right, so good. With that preamble out of the way, let me start then by developing a method to reveal the multipolar fluctuations in these materials, and then go on to look at the transverse field effects. All right, so what I specifically want to do is measure the multipolar susceptibilities. And I'm going to do this via an adiabatic caloric response, which we heard about from Elena as well. Oops. So first of all, though, why should I even care about susceptibilities? Why am I not talking about, well, what's the broken symmetry? So first of all, susceptibility attests to the presence of fluctuations from the fluctuation dissipation theorem. So if, I don't know, from some theoretical perspective, you care that there are octopolar fluctuations in a material, how do you know when I hand you this that there are such fluctuations? You better have a way to measure that. The second reason is this is a quantity that's non-zero for all temperatures. So praseodymium, vanadium, aluminum orders at 0.6 Kelvin. I'm not about to show you data down to 0.6 Kelvin, but I can still show you that there's a diverging susceptibility. So this is a physical quantity that's defined at all temperatures. You're not just probing the symmetry of the broken symmetry state. And then lastly, the divergence can be compared to other competing symmetry channels. So a system doesn't have to order with a magnetic octopole. It might order with a quadrupole, but I can ask how close did it come? And then maybe what can I learn about designing similar materials? Right. So that's why I think one should care about susceptibilities of these higher rank multipoles. Right. So what's the idea? You want to measure a susceptibility. Well, you know this is defined in the limit of a vanishing effective field. So the first thing is we have to apply the appropriate conjugate effective field. But now what I'm going to do in terms of measuring the response is not to measure the induced moment, because that's actually quite complicated for some of these. What I'm going to do is an equivalent, but in some sense different thing, which is to measure the change in entropy. And let me sort of show you how that works. And to really understand how this works, so this is good old-fashioned thermodynamics. So to give you a sense of how that works, let me consider the more familiar case of the magnetocaloric effect, and then we'll look at these other cases. All right. So let's briefly talk about magnetocaloric effect and thermodynamics. So any material will have a sort of an entropy landscape as a function of whatever tuning parameters you have. So here's entropy is a color scale as a function of magnetic field and temperature. And it doesn't actually matter what material I'm showing you for this for, but actually it is this thulium vanadate, right? Because we know a magnetic field will split that doublet. This is a calculated entropy, but you can measure that too. And you can imagine parking yourself somewhere on this field temperature landscape. Maybe you park yourself here. And maybe I'm holding this sample just with a couple of very fine Teflon wires, so it's hardly connected thermally to the environment. And I can imagine now oscillating the magnetic field. And if you're doing that in a way where the system cannot exchange heat with the environment, which means you're going to oscillate the field faster than the characteristic thermal relaxation, such that the entropy is constant, then the system is going to move up and down a constant entropy contour, one of these black lines, which means there'll be a temperature oscillation. Right. Usually, when you talk about magnetocaloric effect, what people are doing is parking at one field and just turning off the field. And you just sweep field. Actually, this is how you should measure magnetocaloric effect. No one else seems to do this, but this is a really neat way to measure magnetocaloric. And you do that across the whole entropy landscape. All right. So partial derivatives, dt dh at constant entropy is ds dh over ds dt. S is the entropy. I apply a Maxwell relation, so ds dh is the same as dm dt. And now maybe you can see where I'm going. Right? So in the weak field limit, the magnetization is h times the susceptibility. So the dm dt gives me h times d chi dt. In other words, I measure this physical quantity, dt dh, and I'm going to learn about this physical quantity, the temperature derivative of the magnetic susceptibility. All I have to know about is the heat capacity, and it's defined in the limit of vanishing field. So the heat capacity in zero field, right, that's straightforward. And if I'm away from the phase transition, it's not doing anything exceptional or singular in any sense. So all the singular behavior that we see is coming from the susceptibility. All right, and, I suppose I should say, all right, you can do something somewhat equivalent. So the entropy here, right, that's even in field. It doesn't matter which direction of field for splitting this doublet, for example. And you can quickly show that the coefficient is d chi dt. So the ds dh gives me h times d chi dt. There it is. All right, and we can do something very similar for quadrupoles and octopoles. Right. As an aside, this prescription really works. So this is temperature and field. And now the color scale is the temperature oscillation for a given field oscillation at a given frequency, which is high enough to make this effectively quasi-adiabatic. And now this prescription just asks me, all right, so this is defined in the limit of vanishing field. So I take a cut at vanishing field here, multiply by the heat capacity, and I get d chi dt. If the susceptibility is following a Curie-Weiss behavior, d chi dt is 1 over t minus theta squared, and that's what you observe. Right? It's a foolish way to measure susceptibility, because we've got other ways to do that. But this is just to say thermodynamics works, and we can do something similar for the cases where I can't measure the susceptibility by measuring the induced moment in the same way. All right. So now I go back to my little table of dipole, quadrupole, octupole. But now I'm going to look at the entropy and the adiabatic response. So we've looked at the dipole. The magnetic entropy goes like h squared times d chi dt. Because the entropy varies with field, it means you want to look at the field derivative of this. So that was the magnetocaloric effect. And we saw that ds dh is h times d chi dt. Good. I measure this, and I learn about this. For the quadrupole, I'm going to have exactly the same thing. So field squared, there's a coupling coefficient here, times d chi dt, but this is now the quadrupole strain susceptibility. Because the entropy varies with strain, it's not now the magnetocaloric effect, but the elasticaloric effect, which we heard about from Elena. And now, right, ds d epsilon in the numerator is epsilon times d chi dt. So again, now I'm going to measure this. I know about the zero strain heat capacity, and I learn about the quadrupole strain susceptibility. And the octupole should be obvious at this point. So I've got field squared times d chi dt, but this is now the octupole susceptibility. I have an entropy that varies with field or strain, so I could actually measure either of these, but it turns out a whole lot easier to measure the field dependence of the elasticaloric effect than the other way around. So dt d epsilon, the elasticaloric response, is going to be linear in strain, so linear in strain, but I've got something which is quadratic in field, and so all I have to do is measure this, look for the linear response, and then measure that for a sequence of fields, measure the zero field heat capacity, which again does absolutely nothing in this regime, and I will get the octupole susceptibility. All right, good. So we've all heard about these Razorbill strain cells that one uses to do this. This is the sample sitting here connected to this island. This is shown schematically. There's the island underneath the shield of these piezoelectric stacks. You change the voltage on the piezo stacks, you change the strain state. You can apply a DC strain and then an AC offset. Typical AC offsets we use are around 10 to the minus 5. So these are small strain oscillations, and you're measuring small temperature oscillations at the same time. And I think we had a question in Elena's talk about, well, how are you going to guarantee this is adiabatic or at least quasi-adiabatic? So you have to do this at a frequency which is higher than whatever the characteristic thermal relaxation, or 1 over that is. And you can do adiabatic decompression measurements. You can do a DC version, just release the strain and actually measure the thermal relaxation and even confirm that you're in that regime. Okay. Yeah, exactly. So well, that depends on the material. So for the materials that we look at in the temperature regime that we look at, it's tens to hundreds of hertz. Right, well, what you do is you do a frequency measurement, and you'll find something which looks, if this is the delta t of the oscillation that you're looking at as a function of the frequency, zero frequency, nothing, it's isothermal. Rises up. Problem is, I've got to get heat into my thermometer, so somewhere over here, I've got too high a frequency, I don't get heat into the thermometer, so this does that. And what you want is to have these sufficiently far apart. Let's say this was rising up to here, that I'm at least quasi-adiabatic. Okay, and what I'm indicating here is a simulation, a finite element simulation with all parameters from a material we've measured. It's not the Thulian vanadate, it's something else, but that doesn't matter. And you can see the temperature of the sample changing and some heat leaking out into the environment. We just want to do this at a high enough frequency that we're at least, oh, I can't use this point, at least somewhere up near the top of this dome. And we measure this frequency dependence to make sure we're in that regime. Lovely. All right, so for the thulium vanadate, Here's more of a schematic. These are the jaws of the strain cell. Here's the crystal. It's a beautiful yellow color. Here's a heat pipe to the thermometer. So in this particular case, I'm not using a thermocouple. I'm using a resistive thermometer. And you don't want elastoresistance effects from the thermometer, so you separate the thermometer so it's not strained. And you connect this to some bridge, and you've got a very sensitive way to measure the temperature oscillations, which are of order a millikelvin or less. And we're going to apply the stress, uniaxial stress, along the 110 direction. So the crystal axes here are at 45 degrees. That means you will induce an antisymmetric B2G strain. That's the right strain to couple to the order parameter. And symmetric A1G strains. But for this doublet, the A1G strains, all it does is change the crystal field splitting to these excited states. It doesn't split the doublet. Only the B2G strain splits this. Again, this beauty of these doublets, reducing the number of possible things it can do. All right. So how does this look? So here's our recipe. So dt d epsilon is linear in strain and proportional to the susceptibility. That's for vanishing fields. All right, so here's dt d epsilon as a function of temperature. And each one of these curves is a different offset strain. And here, this was the frequency of this particular measurement. OK, good. So this funny shape is coming from that entropy landscape. It's actually very similar to the entropy landscape of the field dependence that I showed you because you're just splitting this doublet. It's the same sort of thing. My recipe was to ask, where is this linear? So let me take a series of cuts. So the same data, but now as a function of strain. And the color scale is just the temperature. Ask where that's linear, and it's actually a fairly wide strain range. And take the slope of that. So that slope is all of this. And then all I have to do is multiply by the heat capacity, which is just coming down, and at this temperature range doing very, very little. All right. So that's what I'm showing by the black dots here as a function of temperature. So this is the slope of dt d epsilon multiplied by the heat capacity at constant strain, right, which is just the zero strain heat capacity. You get something here which seems to be growing. In fact, it's diverging, and if you fit that, you'll find it exactly follows the anticipated Curie-Weiss functional form, just like the magnetocaloric behavior did. And if you go one step further, you'll also see this follows the same temperature dependence as the temperature derivative of C66. So let me briefly comment on that. So if I go back to my thermodynamic relations, so dt d epsilon was ds d epsilon over ds dt. All right, well, this bit's heat capacity. That was the easy bit. ds d epsilon, if I look at the order of derivatives of the free energy, I can take, instead of s is df dt, I can take the strain derivative first. The strain derivative of the free energy will give me epsilon times C66 and take the temperature derivative. All right, so C66, good. That's something that Brad Ramshaw can measure, or anyone can if you want to do this sort of thing. So you look at some phonon mode or some propagating strain thing, which will involve C66 and maybe some other elastic stiffness components of the elastic stiffness tensor. These guys just gradually soften. There's not much happening, or gradually harden. There's not much happening there. All the temperature behavior is coming from C66, which is softening, remember, from these quadrupole fluctuations. And indeed, you get exactly the same temperature dependence. All right, good. Thermodynamics works. Right, so it's parameter-free, but the only thing is, the point I made down here, I can't point with this. So this is quasi-adiabatic. So what we do is compare at one temperature and normalize either, actually the way we do it is you normalize the entropy because you know you've got KB log 2, and then you're done. And so the temperature dependence is the piece you're looking at, and that's identical. Yeah.
But again, these two quantities with the same coefficient.
Yeah, exactly. And that's the point I'm making. It's not, because this is not perfectly adiabatic. Yeah. And actually, look, there's another thing. So, right, technically, we're measuring the dynamic quadrupole susceptibility. So there's another point, right? This is measured at gigahertz, Brad, and we're measuring at 200 hertz. So actually, so this is just telling you there's no interesting frequency behavior in this material, but you can bet your bottom dollar that other materials will. And so that's where I think the advantage of this is we can start looking then at frequency dependence for cases where there's glassy dynamics. That's some of the stuff we're doing. Good. All right, so that was the quadrupole. Let's do the octupole really quickly, and then I'll do my transverse fields. Right, the octupole, we saw that we had 3 allowed multipoles, 2 electric quadrupoles, and this magnetic octupole. Right, so how do we apply the composite effective field? So remember, this is a cubic system. So I can show my cubic system as a cube, but of course we're going to cut a narrow bar. We're going to apply a uniaxial stress along the 1, 1, 1 direction, which will induce epsilon xy, epsilon yz, and epsilon zx. And we're going to apply a magnetic field in the 1, 1, 1 direction as well, and that induces hx, hy, and hz. Right? So that's how we're going to do this. But now here's the total beauty of this system. That magnetic field, you might worry, is going to induce a dipole. And this strain, you might worry, is going to induce a quadrupole. But this doublet doesn't permit those multipoles. It only permits either these quadrupoles, which we're not coupling to linearly, or this magnetic octopole. And so this combination of physical quantities, which could couple to other lower rank multipoles, only couples in this combination to the octopole. All right. Okay, so we do the same thing. This is our recipe. dt d epsilon goes linearly in strain, quadratically in field, proportional to the octopole susceptibility once we know the zero field, zero strain heat capacity. All right, so this is the temperature oscillation that we'd looked at, same idea. As a function of strain, here I'm showing this for one particular temperature, and each of the colors is then just different magnetic fields. So you can already tell there's a strong field dependence, yay, rare earths. Well, a strong strain dependence as well, yay, rare earths. Just yay, rare earths. Ask the linear part of this. This is then showing the linear part of that. Now as a function of field for just 3 representative temperatures, you get some strong field dependence, fit that to a quadratic form. So that's now this quantity, and then multiply by the heat capacity, and you get something which, again, diverges, again, with a Curie-Weiss form. Don't pin me down on the Weiss temperature. I'm not going to get into details of that. But this is coming from diverging octopolar fluctuations. That blows my mind, that you can, something as complex as a fluctuating magnetic octopole in a chunk of shiny metal that I show you, you can actually be sensitive to that. So. No, it's not at all. And if we were talking more in depth around this and zoom in here, actually this flattens off, you get multipolar Kondo effect. Yeah. So Jörg is completely right. I mean, the things that motivate us is when something isn't actually just, but I just want to get at the main point. Like, we know what a doublet does. This is doing what a doublet should do. Right. Okay, so at least in this system, there are certainly octopolar fluctuations, which at one level you know, but now you can see. Right. All right, so now let's do the bit that I'm perhaps more excited about, transverse field effects. And I'm going to specialize to Thule invalidate, but you can imagine doing this in any of these multipolar systems. All right, so we're familiar with the transverse field Ising model. Take the tildes off these operators. In a mean field model, this gives me my z-axis order, and I can, of course, apply a field which is transverse, induces an operator which doesn't commute, quantum fluctuations, quantum phase transition. Right. Now I put a little tilde back on top of these. These are my operators for my pseudo-spin. They're still the Pauli spin operators, which are just the Stevens operators condensed down to operating on just this doublet state. All right. If this is describing the quadrupole order, I know what these two effective fields are. One is the magnetic field, and one is the orthogonal strain. This is a figure drawn by Akash Maharaj. He's one of Steve's students a long time ago. The symmetry of the Thule invalidate has an XY symmetry pneumatic, so this would be x squared minus y squared strain. Right. So I could look at either of these, and I'll talk about both. But let me start by looking at the field dependence. And I want to look at what happens as you tune through this quantum phase transition. And in fact, what I want to follow is the shape of this phase boundary as you approach this point. All right, so I want to map the phase boundary, and the physical quantity that's best to do that is the longitudinal magnetic susceptibility. And if I pause and think, all right, so this is ordered with a quadrupole, magnetic field was a transverse field, so the longitudinal real magnetic susceptibility is the transverse susceptibility for the pseudospin. All right, why is that the right physical quantity to look at? So if I sketch the atomic energy levels of one of these ions, and imagine that this is it's at t equals 0, in the quadrupole ordered state. So that doublet is split spontaneously, and as a function of energy, this is, if you like, quadrupole up and quadrupole down. And now I apply the transverse field. You know what that does. It admixes these states, and you progressively develop a dipole. And one of the features of the transverse field Ising model is that that splitting remains constant as a function of the transverse field until I no longer have any quadrupole, right? That's your phase transition, and now you have only dipole, right? So that's the energy levels of one of these ions. If I ask what the magnetization is doing, the magnetization is rising as I mix the dipole in here, and then at t equals 0 is constant. And if I were to look at this at a higher temperature, the spontaneous splitting of these two states is less. I have a smaller quadrupole moment, but I have exactly the same thing. It's just now the critical field is at a lower field. But the magnetization will rise linearly, actually with the same slope. I'll again have a kink, but now it takes longer to rise up to saturation because I have thermal population of these states. All right, so that's what we anticipate the magnetization does. You can calculate the susceptibility. So this is now just calculating the susceptibility for a mean field model. All right, good. So here at high temperature, so this is susceptibility as a function of field. At high temperatures, and each of these curves are different temperatures. High temperatures, there's the kink that's here, and then takes a while for the susceptibility to arrive at this value. And at low temperatures, you've got a sharp step that corresponds to this. All right, so why do we like to measure the susceptibility? It's a physical quantity which gives the largest signal at the lowest temperature, whereas if I were measuring a caloric property, heat capacity, something like that, the entropy you remove is getting smaller, smaller, smaller. So that would be the wrong thing to look at. This is the right thing to look at. But it's more than that. You can measure the susceptibility directly. I don't have to measure magnetization. I can just do a mutual inductance measurement. So I'm going to let nature take the derivative for me, which is always something you want to do if you can. All right, so here's how that looks. So this is the susceptibility as a function of field. Each of these curves is a different temperature. This straight section here is that sharp drop, but where, because we don't have a perfectly ellipsoidal sample, the field at different points in the material is slightly different, so this is kinked over. If you zoom into this, right, so first, green is high temperature, blue is low temperature, good, it's moving to the right, that's kind of what we were anticipating. So you go to lower temperatures, the critical field moves to the right. But if you zoom in, and I look in here, and it's a little hard to tell from the colors, the phase transition moves to the right, then comes back to the left. A little bit strange. We took the samples then to the high B over T facility. You can measure that down to 10 millik, actually to 5 millik. And if you zoom in here, you'll just see this keeps marching back to the left. This is a really weird phase diagram. If I plot that, so this is temperature versus field. The ferroquadrupole order sitting in here. This is the disordered effect, this disorder system. This is the back bending that we're looking at. But if I blow that up on a log scale and zoom in here, this is what that phase boundary is doing. And you can just as equivalently do a susceptibility measurement at constant field, and you'll see this go from disorder to order to disorder. That's a really weird phase diagram. All right, so what's going on? Well, it's all about the rare earth still, but these are hyperfine effects. This is the thulium nucleus. So it turns out thulium has a single isotope, a single nuclear isotope. We're lucky there. Holmium is the same, actually. That has a single isotope. The beauty of thulium is that that nuclear moment is a spin 1/2. And even I can work with 4-level systems. It gets a little more complex beyond that. That hyperfine interaction is about 40 millik. And what that means is these are not, if I go back to the sketch I had where these were electronic singlets, this is no longer an electronic singlet, it's an electronuclear doublet. So if I could zoom into that, I would find that there are two states, electric moment up, and nuclear moment either parallel or anti-parallel with a splitting given by some multiple of this. All right, so as you cool through that energy scale, now the electronic moment, the quadrupole is not only seeing the externally applied field, but it's also seeing the hyperfine field from the nucleus, which is destabilizing it too. So it requires a smaller externally applied field to completely suppress the quadrupole order, and that's why this bends back. If you want to see that in equations, so we can go back. I've taken off the tildes here because I couldn't be bothered, and I've rotated my basis, and I've rotated my basis for the following reason. I just keep getting confused by a z-axis magnetic field being the transverse field, so I'm going to rotate my basis so z actually is the transverse field. So this is going to be my z-axis real magnetic field, and so I'm going to order in the y direction. That's the quadrupole order. If I induce a z-axis spin, then I should consider spin-spin interactions. Essentially, these are dipolar. And I also have to include the hyperfine interaction. All right? If I turn that into a mean field model, good, so we know what the quadrupolar part looks like. This gives me the quadrupole order, and we know what that coefficient is. All three of these terms give me something which is proportional to SZ. And so I've got the transverse field, I've got the dipolar interaction, and the hyperfine interaction. And it's clear then that these two things are adding on top of the applied field. Right. There is a kind of acute thing about this, which is that the expectation value of SZ doesn't change with temperature. So actually this, although it's adding to the field, doesn't change the shape of the phase boundary. But here you've got an extra internal degree of freedom where the expectation value of the nuclear moment actually does change with temperature as you cool through that. And so if you do a quick calculation, so we know the values to use for these just from measurements, separate measurements. These two curves are turning on the dipolar interaction, but it doesn't change the shape of that curve. It doesn't actually give you backbending. Both of those cases, you turn on the dipolar, the hyperfine interaction, you get the backbending, and that's how you can describe this. All right. So here's an interesting, we were talking about lithium holmium fluoride earlier, right? So these are two materials that we hold and love for their simple quantum phase transitions. Right, thulium vanadate is Ising ferroquadrupole order. Lithium holmium fluoride is Ising ferromagnetic order. Both are tetragonal, both have the same irreducible representation, crystal field ground state. In the case of the thulium vanadate, the hyperfine interaction enhances the transverse field. That's why you get the backbending. In the case of lithium holmium fluoride, be a little careful, this is temperature and transverse field, so the axes are switched. But in this case, the hyperfine interaction strengthens the magnetic order. So here, the hyperfine interactions are this. So two sides of a very similar coin. All right. So as a final comment, we might ask, what about the nuclear degeneracy? So without hyperfine coupling, we had an electronic singlet in the ordered state, quadrupole up. That quadrupole up, I can write as just a linear combination of dipole on each of this, on this side. So it's a non-magnetic electronic singlet. And I've got the degeneracy of the nuclear moment up-down on every side. All right. That nuclear moment has a value of about 0.23 nuclear magnetons. There is dipolar coupling between these. It will order, but nuclear order without some help happens at a microkelvin or less. On the other hand, with hyperfine coupling, something very special is going to happen. So now, good, there's an electronuclear doublet. That means that for each of these cases, nuclear spin up, nuclear spin down, I add mix in some of the electronic state. But for nuclear up, the amount of up and down electronic state, the coefficients alpha and beta here are different. Because of the hyperfine interaction, I add mix more of the spin up. And similarly, for nuclear down, I add mix more of the spin down. So this state is initially degenerate, but the effective moment associated with it is enhanced because I've co-opted this 4F moment. And these 4F moments can interact through the dipolar interaction and through exchange. And that enhancement factor is about a factor of 770. Right. So now, at a mean field level, you're going to anticipate nuclear order at a temperature of about a milli-K rather than the temperature of about a micro-K. Okay. So now this is just an anticipated phase diagram because we haven't measured to that temperature. But on some log scale of temperature versus field, right, we know what the ferroquadrupole order is doing, but now we have to put a critical point here for the nuclear order assisted by the 4F. That doesn't profoundly change this phase diagram. The color scale here is just the expectation value of the nuclear moment, and you can see, all right, develops a spontaneous moment here, and in the presence of a field, you have a finite moment at all temperatures. The backbending happens when this becomes reasonably large. We understand all that, but there's no extra phase transition, so I've just put one critical point on there. But if I now go to the other effective transverse field, which was the orthogonal antisymmetric strain, that doesn't break time reversal symmetry. So now in the presence of that effective transverse field for the quadrupole order, I can still break time reversal symmetry and have the ferromagnetic nuclear order. So now the anticipated phase diagram, calculated at a mean field level, involves, all right, good, so this is the ferroquadrupole order suppressed by the transverse effective field, the orthogonal antisymmetric strain. This is the critical temperature for this electronuclear order. But that persists as a function of field. And at a mean field level, you would have a tetracritical point involving these two entangled states. And if you were to ask what happens here, again at a mean field level, there's a rather interesting, again, backbending of the ferroquadrupole order. So if I zoom into this point, the ferroquadrupole order comes down. Here's the electronuclear ferromagnetic order. And the reason that this backbends is, as you cool down into the dipolar ordered state, I've co-opted some amount of the quadrupole. The pseudospin has rotated a little bit. So now it requires less of the transverse field to suppress the quadrupole order. And in fact, the temperature dependence you see here is just from the growing order parameter associated with that. All right, that's a kind of a funky phase diagram as well. All right, so thulium vanadate then is an example of electronuclear elastic quantum criticality. And this is, again, a crazy thing. You've got a little, tiny little 4f orbital, which is making the entire lattice go soft. You almost want to reach inside the cryostat and feel, what does it feel like to shear something where there is zero resistance to it? But it's also connected, reaching down to the scale of the nucleus. Across all of those energy scales, this thing is connected. And thulium vanadate is distinguished because of the ferroquadrupole order good by complete ferroelastic instability, but also the interplay of these two intertwined order parameters. So you can get nuclear order in Van Vleck magnets. That part is a known thing. But in those cases, there's no additional order parameter or degree of freedom. But in this case, the splitting of that doublet into these two time reversal symmetry preserving singlets is actually described by an order parameter, and you've got this little pseudospin which is rotating around. All right. So just to try and bring it all back together, so the original theme was strain control of quantum materials. A number of us are thinking about these things and are excited about these things. I think you've heard from a number of us that strain is a valuable means to probe and manipulate them. And I've just specialized to the case of local multipoles, but you can extend these ideas fairly readily. You can imagine different ways that you could take this. I'm rather interested in strain gradients. But as a sort of a parting message, materials, unlike people, should be made to feel the strain. Okay, I'm not even going to read this. Let me just leave up. You know what I've told you because I've just told you it. So let me stop there. Thank you for your attention.
Thank you, Ian, for the great talk. And now we have a time for questions.
An almost obvious question. Has anybody measured NMR in the thulium case?
Yes.
And do you see all the effects of this ordering that you showed?
Yes, so this is Nick Kuro's work. We've worked closely on with him. You can do all sorts of things. So the vanadium nucleus has a 5/2 nucleus. So that's a quadrupolar moment. The thulium nucleus doesn't have a quadrupole moment. So you can't do thulium NQR, right? But you can do the vanadium NQR, and yeah. So it behaves how you expect.
Okay, thanks, Ian, for a really nice talk. So my question, I think, is related to Jorg's about just the temperature dependence of the susceptibility. So even if you can't resolve exactly the exponent, if it's Curie-Weiss or not, can you see a change as you approach, the quantum critical point in the temperature dependence of the of the susceptibility?
Right. So actually, I wasn't showing. So as I approached the quantum critical point here, we were measuring the transverse susceptibility. The longitudinal susceptibility would be elastic-caloric behavior. These are things that we're doing.
I see. Okay.
Yeah.
Thank you.
Hi, Ian. This is probably crazy theory talk, but...
well, you're a crazy theorist, Raphael.
Exactly, so it's perfect. Is there in this class, I know you looked a lot in this 4F, 5F, 4F systems. Is there like the counterpart where the non-Kramers doublet wants to order in the dipolar channel, but the nucleus is 3/2, so you have the quadrupolar moment in the nucleus? That would be the counterpart of these, where the...
Yeah. I don't know, but so lithium holmium fluoride, holmium has 100% abundance too. So only a few of the rare earths have 100% abundance. So that's one semi-issue. For holmium, it's a spin 7/2. Well, you saw the Rosenbaum's mean field calculation for that. It's at some level more complex, right? Your Hilbert space is a lot larger. But I'm not aware of one which would work in the way that you're saying.
And if I can just, the second question is, when you talk about the octopolar order, right?
Yeah.
You also show that the one other conjugate field is the HX times HY times HZ.
Yeah.
Couldn't you measure like a nonlinear magnetocaloric effect
Yeah.
to also get that? And
Yeah.
Is this easier or?
No, it's not.
It's not.
Yeah. So we tried this exactly, and technically, right, we're applying a field as well. So you got to be a little bit careful with that. But yes, so that also is a field. So we're measuring the, whatever you want to call that, the susceptibility towards that thing. Yeah. But that's cubic in field. So for small fields, how do you define small? But all we look at is when does this sort of stop being quadratic, and over 10 Tesla is quadratic. So, yeah.
Hey, Ian. So there might be easier ways to do this, but I'm a neutron scatterer. So I know that if you start to polarize the nuclear spin, you will change the nuclear cross-section for neutron scattering. And so you could look at diffraction peaks which had a large thulium component, and if the nuclear spin starts to polarize, you should change the nuclear intensity.
Lovely.
Doing it at 1 millikelvin is a bit of a challenge, but I wonder if you ever thought about
I haven't,
doing those things.
but we have huge crystals, so we'd worked with Young Lee before just to look at the order parameter. So literally just lattice parameters as a function
Right,
of
but
magnetic
you could look
field.
at high Q
Yeah.
and get away from any dipolar order and just look at nuclear peaks and see whether you get an enhancement.
No, this would be lovely. I mean, at the moment, my interest is in using nuclear demagnetization to actually cool this to low enough temperatures to try and see the order. But anyway.
But also the incoherent cross-section spin incoherent cross-section would drop as the nuclear
cool.
spin would order.
Would that be interesting just from a straight up scattering perspective?
It's worth looking, but I think the temperatures are a challenge. But if you think you have some, say, finite polarization of the nuclear ground state at 30 millikelvin.
Oh yeah, 100% for sure. So all this backbending happens about a factor of 10 larger than that splitting, and it finishes about a factor of 10 less than that. So the splitting, call it 50 millik, around roughly 500 millik is where you begin seeing effects, and it's all done by 5 millik.
Interesting.
Yeah.
Okay, thanks.
Oh, okay.
Do we have any more questions? Yep. If not, let's thank our speaker again.